Welcome back to the tutorial number 5. This series built a large language model from scratch. At this point, you know how to prepare the input text for training the large language model by splitting the text into individual word and subword token, so which can be encoded into vector representations embedding for the large language model. Now we look at an integral part of the large language model itself called the attention mechanism. So you know that we have the three stages of building the large language model. In the stage number one, we have the data preparation and sampling. Then we have the important one that's called the attention mechanism that we are going to discuss in this tutorial. Okay, now we need to know that what is attentions in the language model. So now we can take the pen and paper. You can also take the pen and paper. So the question is about what is, let's say, what is attention, let's say attention in language model, let's say language model. So unlike here the traditional model that see the word in isolations, or attention allow the language model to consider the context. See the word called context. Okay, so the traditional model I am talking about the RNN, the recurrent neural network. It's also one encoder and decoder types of models. Now, the game changer for the natural language processing field came in 2017. So, how in the papers called the attention is all you need. Attention is all you need. Introduce the attention mechanisms. See, it's introduced a new mechanisms called the attention mechanisms in 2017 papers. So this paper proposed a new architectures called the transformer. That's called the transformer. So unlike the older model like the RNN that already talking about the decoder and encoder only models, as well as the CNN. So transformer using here this attention mechanisms. So by solving many of the problems of the traditional model, transformer, or you can say the attentions, have become the foundations of many of today most popular large language model like the GPT. I mean, I am talking about the chat GPT. You can say the chat GPT, which are using the transformer itself in the behind the scenes. Okay. Now, how does actually attention work? Okay. Now that's our next question. So how does attention work? That's the important question, right? So let's consider the word called bat. I'm just taking here a word called bat, and using this word, I am going to write here two sentences. So let's say I have the one sentence. I mean, first one is called, let's say, swing the bat. Let's say swing the bat. The second sentence, let's say, the bat flew at night. So you can see that in the both word it have the similar word called bat. This bat and this bat. So in case of the traditional the embedding method, it will assigning here a symbol. I mean the single vector representation for this bat. Let's say if I am using here this RNN, or I'm just going to using here any kind of traditional model for the language translations. So assigning here and single vector representation for the bat. If I use here any kind of traditional model, so let's say if I going to pass it to the vector representations, it will obviously give the same token as this the sentence number one and the sentence number two as well. So in the case of bat, it will, let's say it will give the token ID the 10. Same thing for 10. But in the both sentence, the word bat is not similar. It having some different types of context value. Okay, so by limiting your the ability to distinguish between these meaning that you can see bad, so attention mechanisms however addressing this by computing here this content dependent weight. See, content, let's call the content, so not content, actually context. Okay, it's called context dependent weight. See what I am talking about. I'll recap it again. How does attention work? So I'll consider here a word called bat. And I write here two sentences: swing the bat and the bat flew at night. If I using here any kind of traditional model, I mean I'm talking about the language model, so it will give here this bat and this bat as the same vector representations. But the attention mechanisms it addressing these two words by computing here one context dependent weight. That's mean it will try to catch up some kind of meaning or some kind of relationship. So what actually happening these attention mechanisms? So the attention mechanism is try to surrounding this word. Let's say we have the word called swing, then you have the another word called flew. So what actually happening in the case of attention mechanisms, it will analyze the surrounding word, the swing, and versus the flew, and it will calculate here the attention score. See the most important one, it's calculate here the attention score that determine the relevance. Okay, that determine the relevance, I mean it have the connection or not. So this score are then used to weight the embedding vectors in case of the attention mechanisms. So resulting in distinct dependency for the bat. If I have the bat, let's say the first word bat at as a sport tool, I mean I'm talking about the cricket bat, and the second bat in the sentence number two, it's actually representing as a flying creatures. Okay, it's as a flying creature, like. So that's mean in case of this bat, it will give here one high weight, it give here one high weight of the swing. Okay, so in here it will give here one high weight of the flew. That is happening in case of the attention mechanisms. But if you are using here any kind of traditional model, so it will assigning here the similar types of context, I mean similar types of actually vector things, right? Sorry for my bad, actually one call is coming. Okay, so see that you discuss about how does attention work. So this allows the model to capture the semantic meaning and improve its comprehensions. So if I draw here one kind of diagram, okay, let's say I have the word called swing the bat. So let's say swing the bat, then I have the another word called the bat. Okay, the bat flew at night. That's at night. So if I pass in this two word in the attention mechanisms, or you can say the attention embedding. So let's say embedding. So it will considering here, it will give the high weight for this bat as a swing and this bat as a flew. Okay, that's mean it have one context aware vector. It's having the one context aware vector. Both this word it have if you using here the attention embedding, but if I using here the traditional embedding that is used by our sequence to sequential models, sequence to sequence model, let's say traditional model, it will just give it to here this bat and this bat at the same context. That's mean it don't have any no context vector. You don't have any kind of attention score. That means this bat and this bat is similar in case of the traditional model. So this is the big problem in the case of the traditional models. And attention mechanism is right now cool, right? Now let's see what are the problems. No, okay, no, not problem actually. Now let's see what are the types of the attention mechanism. I mean, how many types of attention mechanism is actually available. So there are four types of attention mechanisms actually available. So we can say that there are four types of. Okay, I'm little bit curious. Okay, so there are four types of attention mechanism are available. The first one is called the simplified attention mechanisms. The second one is the self attention mechanism itself. Self attention mechanism itself. The third one is about the causal attention. Let's say causal attention. And the fourth one is the most important one that is used in the transformer. That's called a multi-hat attention. Let's say multi-hat attention. If you don't know what is the multi-hat attention and how can you implement it, you can go and check out the videos about the transformer, and I already make a video about that. How can you code it from scratch? Now, what is the simplified attention mechanisms, or what is the self attentions, what is the causal attentions, and what is the multi-hat attention actually? So if I go to the book, that you can see coding attention mechanisms. So you can see simplified self attentions, then self attentions. Okay, it should be the simplified. Okay, it should be simplified self attention mechanisms. Okay, it should be the simplified self attention mechanisms. So that you can see. So it's a simplified self attention technique to introduce the border area. I mean the border area of the sequence. Then the self attentions. So self attentions with a trainable weight. I mean in the case of self attention, it having that trainable weight that from the basics of the mechanism that is used in the large language models. The third one, also important, that's called the causal attentions. So this type of self-attention that is used in the large language model that allow a model to consider only the previous and current input in a sequence. See, it will consider only previous and current input in a sequence, ensuring the temporal order during the text generation. That's when they're talking about the marks. They're talking about the marks. And then the fourth one is called the multi-hat attentions. It has the query key and the value. So an extension of self-attentions and the causal attentions that enable the model, see, that enable the model to simultaneously attend to informations from different representation subspace. That's what actually using here the query key and the value. Then it also using here the cosine of the signs in order to getting here the vector representations. Okay. So there are also some kind of problem with the modeling long sequence. Okay, because before the large language model, so there are some kind of model is also available for the language translation. So it's one kind of called sequencing. You can say the sequence to sequence. So in case of sequence to sequence model, it having some kind of problem. And you can see the problem with model sequence. Now let's see the problem with modeling long sequence. So before we dive into the self-attention mechanisms at the heart of the large language models, so let's consider the problem with pre-large language model architectures that don't include any kind of attention mechanisms. I mean, what if you don't have any kind of attention mechanisms? So let's take one example. So I'm taking one examples from English to Bangla because I am Bengal itself. Okay. So let's say, can you help, let's say help me to translate, let's say translate this sentence, let's say this sentence. So let's say in Bengali it can be তুমি কি আমাকে বাক্যটি, okay, let's say বাক্যটি অনুবাদ করতে সাহায্য করতে পারো বা সহায়তা করতে পারো, লেটস সে সাহায্য করতে পারো, লেটস সে ওয়ান interrogative sign. Okay, so can you help me to translate this sentence? If I translate it in Bangla, তুমি কি আমাকে বাক্যটি অনুবাদ করতে সাহায্য করতে পারো বা সহায়তা করতে পারো? So see the can. Okay, cans mean if we translate it to Bengali, it's mean para. Okay, I mean do something. Okay, so it is go on here, and you, it's go on here. Help, it's mean shahayata, I mean shahajjo, that you can see. So if I going to convert this to word by word sequence, to translate it from English to Bangla, it's not possible. It may be have some kind of grammatical issue. It having some kind of grammatical alignment issue. Okay, alignment issue. That's mean word by word sequence. It's not correct. It's not correct. So if I go to translate it from Bengali, I mean English to Bengali, I need to change the positions of the word. So same thing in the book that they actually discuss on here. See, if I taking one example, try to convert it from English to German. Can you help me to translate this sentence? So you can see here this is the correct translations, and then certain word in the generated translation record access to word that appear earlier or later in the original sentence. That's mean you need to accessing here the previous sentence as well. But if I'm going to using here this word by word translations, it may be hence some kind of grammatical alignment issue that you can see. That you can see. That's mean the problem with the modeling long sequence is correct. In the case of word by word, okay. So that's why it will to addressing this issue. So you cannot translate the word by word that you can see. So it is common to used here a deep neural network with two submodule called encoder and decoder. Encoder and decoder. So the job of the encoder is to first read the text and process the entire text, and the decoder then produce the translated text. I mean encoder, decoder, RNNs. Now to see that the work. I mean how actually RNN actually work. Okay, because RNN only have the encoder and the decoder. Okay, RNN have the encoder. Let's say encoder and the decoder. Okay, so in case of RNN, it have one encoder. So let's say you have the encoder which are taking one text. Let's say text. It will process this text and then it will passing it in the case of context to the decoder, and decoder is finally translating this text. Let's say I'm going to converting them to the English to the German. It will try to do it. Okay, but but if I see the complete architecture of the RNN in case of the I mean the flow chart. So in the RNN, it have first one input text that you're going to passing it over to the encoder. That's the input text. Then we're simply going to pass it to the encoder. Okay, let's say encoder. So the encoder it basically process the text sequentially. See, sequentially. See, the RNN process the text sequentially, and after that it will update. See, it will update hidden state. See, hidden state at each step. See, in RNN, one important term called hidden state. It will capture the memory. It will capture the memory. See, in the case of long sequence, for the word by word, it's not a work because it don't have any the memory. But in case of RNN, it have the hidden state. It will capture the memory and it is also get updated. It also get updated by each iterations, and it will give the final result. It will give the final results. Okay, or you can see the final hidden state. Okay, it will just give it the final hidden state, then it will pass it to the final hidden state. Then this final hidden state is going to pass inside the decoder, and decoder is try to decode the text. Okay, so decoder use these final hidden state to generating the translate text one word at a time. See, one word at a time in the case of RNN. Okay, now here is also one kind of problem. See, in case of RNN, it can just accessing the last hidden state. It can only access the last hidden state. Okay, if I draw it correctly, so if we have one input, let's say if I have the input, let's say we have the input number one, then you're going to passing it to the RNN, and it will produce here the output number one. Okay, And when the input number is 1, we have the hidden state of the 1. That's a hidden state of the 0, so not 1 actually. Then it will get updated. It will get updated. That's a hidden state number 1. That's mean first it have the hidden state of the 0. Then when you passing the first input, it will go inside this RNN. It will process them. It will keep here on output, as well as it will updating it hidden state, or you can say the memory cell. You can say the as a memory cell, and it is getting updated. So if you have the time stamp of 3, if I have the time stamp of the 3, so last hidden state the 3 is going to passing to the decoder. That's mean if we have one encoder, let's say if we have the encoder and we also have the decoder, let's say I have the 3 encoder of the RNN. Let's say encoder RNN. Let's say this is the first encoder of the RNN. Now the second one, let's say encoder. Okay, it should be the encoder of the RNC, the most important one. And let's say encoder of the RNN. So in case of the RNN, we are basically passing here the hidden state in the case of context. In the case of context, to the decoder, to the decoder. Now, in the case of RNN, it can just accessing the last hidden state. It can just access the last hidden state of 3. State of 3. That means it will forget. It will forget the hidden state number 1 and the hidden state number 2. That's mean some of the information is missing. It cannot access the long sequence. It cannot access the long sequence as well. That's also one problem in the case of RNN. Also, one more thing you can see, the encoder process the entire input text into the hidden state that you can see, and decoder is getting confused because it's just getting the hidden state number. That's hidden state number 3, right? So that's allow the neural network to focus on different parts of input sequence. Okay, but in case of the RNN, it not possible. It not possible. So what are the limitations? Okay, I write down some kind of limitations to the RNN. So let's see the limitations of the RNN. Okay, that is I'm going to take it. Okay, now let's see the limitations of the RNN. Okay, let's see the limitations. Let's say limitations of the RNN. Okay, so let's say okay, not here. So let's say limitation of RNN. So there are some kind of limitations. The first limitation is called short range dependencies. Okay, that you already see that it just accessing the last hidden state. Okay, so that's why it has the short range of dependencies. So RNN actually struggle to grasp up the connections between the distinct word if it had the if it is the neighbors. Then the second problem is called limited. It's called the limited parallelism. That's also one problem in case of the RNN because it will processing the information sequentially. See, it processing the information sequentially from here to here and here to here. So it's inherently actually slow because you see that it's just processing all the data one layer to another layer, one layer to another layer, one layer to another layer, just like a CNN. I mean sequential of the CNNs. So it's preventing here the efficient training and it will utilization for the computation resources. So especially for the long sequence. So in the case of long sequence, it's obviously taking time. So it's a bad practice and it taking here the more amount of memory. Okay. Now the limitation number 3. Limitation number is 3 on focus on local context. Focus on local context. Local means actually neighborhood. So if it is near neighborhood, then it can actually easily access it. But if it is far away, So it's unable to access it currently, that you can see, because it just have the final state of the final of the hidden state. So that are the limitations of the RMs. So those limitations hamper the ability of the transformer to to perform the complex tasks like the machine translations. So in the case of machine translation, if I have the long sequence, it unable to perform well, as well as for the language, I mean natural language understanding. So that's why the attention mechanism actually counts. So before the 2017, I am talking about the paper attention is all you need. So there is also one paper is published in 2014 about the BAH Bahdanau attention mechanisms. See, that's been attention mechanism is also introduced in 2014, and after 3 years later on, the attention is all you need paper is published. I'm talking about the transformer. I'm talking about the transformer. Okay. So although the RNA actually work fine for translating the short sentence that you can see. Okay. So but they don't work well for the long text. Longer text, as they don't have the direct access to the previous word in the input that you can see. It can directly access the previous word. The hidden state number one. Okay. That's the basically the main problems. So that's why researchers called Bahdanau, they actually introduced these attention mechanisms in 2014 in the paper. So you can just go on the Google and search it for that. So let's say BAH, that you can see Bahdanau attention mechanism. Okay, okay. The name is not correct. I actually spelling. Okay, it's a U here. Okay, Bahdanau attention mechanisms. Okay, so that you can see. So this is the paper. So I can open in this yet. So that you can see, I can view the PDF. So you can see neural machine translations by jointly learning to align and translate, that you can see from Jacobs University of Bremen, Germany. So you can see the name, the first name of the authors, that is this Bahdanau. Okay. So you can also read this paper. It is published in 2014, that you can see. Okay. They're also talking about the long short term memory. They're talking about the LSTMs. So you can learn about this, that how it actually work. So in case of this Bahdanau attention mechanism, what actually happening, if I go into this book that you can see, let's go on the full screen mode. So if I go down, so it's about the capturing the data dependencies with the attention mechanism that you can see. So in this Bahdanau attention mechanism, it's able to access the hidden state. It's able to access the hidden state number 1, 2 and 3. If I go on here, see, it can just access in the hidden state number 3. But if I using this Bahdanau attention mechanisms, it's able to access the 3 hidden state. Okay, let's say if I have the encoder, let's say this encoder of the RNN, let's say encoder of the RNN, let's say this is the one RNN1, RNN2, and let's say encoder of the RNN3, and you have the decoder. So in the case of Bahdanau attention mechanisms, if I process the text, so I can directly sending here the 3 hidden state. I can access this 3 hidden state. That's a hidden state number 1, hidden state number 2, and the hidden state number 3. I can directly access it from the decoder. That's one important things that is happening in 2040. Okay, 2040, and after that the attention mechanism paper is actually coming. Attention is all you need paper is still coming. If I see it in the book, that you can see, it can easily access it. In this figure, we can focus on generating the second output token. Okay, we can access it from a C. We can also access this though. So this dotted line weight is proportional to how important the input token is for the respective output token. That means you can also calculating here some kind of importance. Okay. So how in the generating the output token, the model have a way to access to all input tokens that you can see. That you can see. So you can also read it from here. So using attention mechanisms, the text generation decoder part of the network can access all input tokens selectively. So this means that some input token are more important than other for generating a given output token. So this importance is determined by so-called attention weight. See, so-called attention weight. So you can see the exact implementation of the Bahdanau mechanism, which is an RNN method outside the book's book. Yeah, we know that. So now let's see what is actually self-attentions. Okay. So the self-attention is a mechanism that allow the each positions in the input sequence to attend to the all positions in the same sequence when computing the presentations, the representation of a sequence. समझ नहीं आ रहा ना, कोई बात नहीं, मैं बाद में समझ दूंगा एक्चुअली. Self attention is a key component of the contemporary LLM based on the transformer architecture such as GPT series. Okay? So self attention just give here some kind of attention scores to the each of the word, so that they can also they can have the same sequence when you computing here the representation of the sequence. Okay, that you can see. So this is the full architecture that you can see. It has the input text, it will have the pre-processing step. So here the topic of the previous chapter, actually we can access it, and it's a previous chapter, I know that, I mean the tutorial number 3 4 we discuss about that. Then you have the self attention module. Okay, so that you need to discuss in this chapter as well. So it's nothing but GPT like decoder only transformer. So the remaining part of the LLM architectures are the topic of the next chapter, because we will discuss it later on. The post processing steps and the output layer, output text. Okay, so that is all about the attention mechanisms in detail. Okay, if you have any kind of query, you can comment below, or you can also send me the message in the link. Okay, so I'll give these links to the descriptions. Okay, so that's it for today. Now I hope you enjoy this full tutorial. So make sure to subscribe our channels. So as well as you can also read this graph that you can see how it will see. If I see this thing, see it have a word called European. Let's say it is stand in the 1 2 3 4 5, 5 and 6, it's stand in the six, number 6. But if I see the translation, it's a 1 2 3 4 5 6 7, you can see the European. Okay, so European, but in here the European is stand in the number 5, but in the translation it stand in the number of 6. That's mean it can also processing the positions, as well as it can processing the grammatical alignment. Okay, that you can see the Bahdanau actual attentions. Okay, if you want to know more about it, you can just read the paper, or you can just search in the Google that what is the Bahdanau attention mechanisms. Okay, this is not the part of our tutorial, but I'll try to creating here a new tutorial about that. What is the difference between all of the attention mechanisms? Okay, so again, that's it for today. Now I hope you enjoy this full tutorial, and make sure to subscribe our channels and share with your friends, so that they can also learn this large language model from scratch. Thank you and bye bye.